You check your phone. July 1st, 2025, a telescope in Rio Hurtado, Chile sends an automated alert. Not another asteroid, not another piece of space debris circling our sun. This one's moving wrong. 137,000 miles per hour. Trajectory bent into a hyperbola. No closed orbit, no return ticket. Third interstellar object ever confirmed entering our solar system. They name it 3 I Atlas. The I stands for interstellar. 3 because 2 others came before. 1 I Oumuamua in 2017. 2 I Borisov in 2019. But this one's different. This one has a tail. This one's a comet. And this one just rewrote what we thought we knew about worlds beyond our sun. If you value documented space exploration and cutting-edge astronomy like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency's official observation reports, published between July and November 2025, and peer-reviewed papers from archives, including Martin Cordner's James Webb Space Telescope Spectroscopy study submitted to the Astrophysical Journal Letters on August 25th. 2025. Now back to the information, July 1st. Atlas Telescope, a dot moving through Taurus. Pre-discovery images traced it back to June 14th in archival data from 3 different Atlas stations and Caltech's Zwicky Transient Facility at Palomar Observatory. By July 2nd, 122 observations from 31 observatories worldwide. David Jewett and Jane Liu at Nordic Optical Telescope confirm clearly active, diffuse coma, not an asteroid, deep random survey in Chile. Lowell Discovery Telescope in Arizona, Canada, France, Hawaii. Telescope at Mauna Kea, all see it. Marginal tail-like elongation, 3 arcseconds. The Minor Planet Center issues designation 3I/Atlas. Also C/2025 N1, interstellar confirmed, hyperbolic trajectory, exit velocity at 1.36 astronomical units from the Sun, 68 kilometers per second, escape speed, one-way trip through our neighborhood, Hubble space. Telescope targets it, July 21st, 277 million miles from Earth, teardrop-shaped cocoon of dust, nucleus buried inside a cloud, size estimate fluctuates. August to 20th observations narrow it down. Diameter between 1,444 feet and 3.5 miles. Most likely under 1 kilometer. Small nucleus, big mystery. Background stars streak in the exposure because Hubble tracks the comet's motion. The nucleus itself, invisible, too dim, too shrouded, but the coma glows. 26,400 kilometers across, according to Gran Telescopio Canarias. Images from July 2nd, twice Earth's diameter. Angular size in the sky. 2 arcseconds at full width, half maximum. 10 arcseconds full extent. August 6th, James Webb Space Telescope locks on. Near-infrared spectrograph, wavelength range 0.6 to 5.3 micrometers. Distance from Sun, 3.32 astronomical units. What comes back shocks the team. Carbon dioxide dominates. Ratio of carbon dioxide to water, 8:1. Highest ever measured in a comet, 6.1 sigma above the trend for long period in Jupiter family comets. Not just high, off the chart. Martin Cordner leads the analysis. Paper hits archive August 25th. Enhanced outgassing toward the Sun. Carbon dioxide, water, carbon monoxide, carbonyl sulfide detected, water ice, dust. Mass loss rates calculated. 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water. The water's suppressed. Something's blocking heat penetration into the icy core. Carbon dioxide sublimates easier than water at these distances. The nucleus might be intrinsically carbon dioxide rich, either exposed to higher radiation levels than solar system comets, or formed near the carbon dioxide ice line in its parent protoplanetary disk. Different star system, different chemistry. August 8th through 12th. Sphere-X mission observes. Distance, 3.2 astronomical units from Sun, 2.6 from Earth. Images at 3 micrometers for water, 4.26 micrometers for carbon dioxide, 4.7 micrometers for carbon monoxide. Water coma, undetected. Carbon monoxide coma, undetected. Carbon dioxide, massive symmetric cloud, extends at least 348,000 kilometers from the nucleus. Brightness declines with projected distance to the power of -3/2. Density falls with radius to the power of -2.5. Mass loss, 70 kilograms per second of carbon dioxide. Water upper limit, 4.5 kilograms per second. Flux at 1 micrometer suggests large nucleus, 46 kilometers diameter if assumptions hold, but that estimate's contested. Surface layer ablation, 1 millimeter thick over 10 years, could sustain the observed outgassing. Thin shell, unknown interior. Gemini South Telescope and NASA Infrared Telescope Facility. Nail water ice, July 5th and 14th. Near-infrared spectroscopy. Fine grains, smaller than 1 micrometer, likely amorphous, possibly crystalline. Swift Observatory catches water vapor and hydroxyl radicals, July 30th and 31st, August 1st, tentative detection. Water ice grains sublimating beyond the nucleus. Distance from core, 4,000 to 10,000 kilometers, not nucleus, sublimation. Volatile ices like carbon dioxide and carbon monoxide ejecting the water ice grains into space where they sublime later. August 21st. Lowell Observatory reports first cyanide detection. Very Large Telescope confirms. Also finds nickel vapor. Atomic nickel. September 7th. James Clerk, Maxwell Telescope measures hydrogen cyanide production. 1.5 times 10 to the 25th molecules per second when the comet's at 2.33 astronomical units. September 14th. Production rate climbs to 4.5 times 10 to the 25th molecules per second. 2 kilograms per second. Cyanide coma, 180,000 kilometers across. Asymmetric. Elongated away from the sun. Visible dust tail, 50 arc seconds. 100,000 kilometers long. Apparent magnitude, 14.2. Color shifts, reddish initially, similar to D-type asteroids, solar system comets, 2 Iborisov, irradiated organic compounds, tholins in the coma. Small dust grains, 1 micrometer radius ejected at 22 meters per second. Large grains, 100 micrometers ejected at 2 meters per second. Hubble images from July, 6 kilograms per second of small dust, 60 kilograms per second of large dust. Similar rate to 2 Iborisov, approaching the solar system but lower than typical distant Jupiter family comets. July and August, coma elongated westward, toward the sun, toward the direction of motion, not a tail, a plume. Sunlit surface heating, ice sublimation faster on the day side, more dust ejected, sun-facing feature. Late August, anti-solar tail develops. Fan-shaped inner coma within 5 arc seconds of nucleus. Brighter on sun-facing side still. Dust tail trails behind. Solar radiation pressure pushes smaller particles. Behavior matches distant comets like C/2014, UN 271, Bernardinelli, Bernstein. September rolls into October. Earth's moving away from 3I Atlas as the comet approaches the sun. Mid-October. Comet disappears behind solar glare from Earth's perspective. Solar conjunction. October 21st. Minimum angular separation 2.59 degrees. Comet at 2.4 astronomical units from Earth. GOES 19. Weather satellite potentially observes it during conjunction. Ground observatories lose sight. Won't reappear until early December 2025. This is the window. Peak activity window. Perihelion, October 30th. 1.36 astronomical units. 210 million kilometers. Just inside Mars' orbit. And Earth can't see it. But humanity has eyes elsewhere. ESA reacts fast. July 1st discovery. Automated detection systems alert them. Ground telescopes in Hawaii, Chile, Australia immediately track it. Hubble observes, Webb observes, Sphere-X observes, but the comet's heading behind the sun. Earth-based assets going blind. ESA has spacecraft scattered across the inner solar system. Mars orbiters, Jupiter probe. They're not designed for comet watching. They're designed for planets, but they're positioned right. And ESA doesn't waste opportunities. October 1st through 7th. Mars Express and ExoMars Trace. Gas orbiter get the call. Turn your cameras toward 3I Atlas. Mars Express launched 2019, orbiting Mars since 2003. ExoMars TGO arrived 2016. Both carry instruments built for photographing the red planet's surface from hundreds to thousands of kilometers away. Now they're aiming at a fuzzy white dot 30 million kilometers distant. October 3rd, closest approach to Mars. 30 million kilometers separation. Mars Express deploys high-resolution stereo camera. ExoMars TGO uses color and stereo surface imaging system, CASIS, 5-second exposures. Multiple frames stacked. Nick Thomas, principal investigator of CASIS, calls it very challenging. The comet's 10,000 to 100,000 times fainter than Mars. Cameras designed for bright planetary surfaces. Scientists unsure what to expect. Results. Fuzzy white dot moving downwards near image center. Slightly blurry. Coma visible. Gas and dust cloud around the icy rocky nucleus. Despite not being designed for targets this far and dim, they capture it. Background stars streak because the camera tracks the comet. Nucleus itself invisible, like trying to spot a cell phone on the moon from Earth. But the coma's there, thousands of miles wide. Glow fades with distance. Full size unclear. Mars Express also fires up Omega and SpyCam spectrometers. ExoMars TGO activates Nomad spectrometer. Light spectrum analysis, chemical fingerprint. Data transmitted back. Colin Wilson, Mars Express and ExoMars project scientist. Though our Mars orbiters continue to make impressive contributions to Mars science, it's always extra exciting to see them responding to unexpected situations, like this one. No confirmed results yet from Mars. Reconnaissance orbiter, despite good positioning. NASA's Curiosity and Perseverance rovers possibly attempted observations early October, but no public data released. Tianwen-1 and HOPE orbiters also positioned well. Silence so far. Maybe data's still processing. Maybe missions 2 focused on primary objectives. Mars observations matter. Closest vantage of any ESA spacecraft, 30 million kilometers. Compared to Earth, 269 million kilometers at closest approach. December 19th, Mars orbiters get a view 9 times closer. Even from that distance, even with cameras not built for this, they see it. They capture the interstellar visitor streaking past the red planet. November 2nd, JUICE enters the game. Jupiter Icy Moons Explorer. Launched April 2023. Destination, Jupiter's moons, Ganymede, Callisto, Europa. Won't arrive until early 2030s. Right now, cruise phase, deep space between Earth and Venus, thermal constraints. Close to the Sun relative to its science phase around Jupiter, no payload activities planned. Then 3. iAtlas appears, opportunity too good to pass. ESA decides, observe, Olivier Witas, JUICE project scientist. All this campaign was unexpected for everybody. Given the uniqueness of these observations, it was decided to prepare this extra observation planning. November 2nd through 25th, JUICE observes 5 instruments activated: camera, near-infrared imaging instrument, UV spectrometer, sub-millimeter instrument, sensor to image neutral atoms, remote sensing only. Distance from comet, 64 million kilometers on November 4th during close passage, 0.5 astronomical units. JUICE positioned to catch 3I Atlas right after perihelion. October 30th, closest approach to Sun. November observations capture peak activity. Comet most active, bright halo around nucleus, long tail stretching behind. Best view of the comet in very active state. Catch. JUICE is using its main high-gain antenna as a heat shield because of proximity to Sun. Data transmission via smaller medium-gain antenna, much lower rate. Data won't download until February 2026. Patience required. But the observations happen. Camera snaps images, spectrometers measure gas composition, sub-millimeter instrument analyzes dust, neutral atom sensor tracks ejected particles, windows kept short, thermal overload risk. Sun's heating the spacecraft, not designed for inner solar system operations yet, but they do it. Test sequences validate commands. Extended sessions follow. Favorable geometry between probe, comet, and Sun through November 25th. Then JUICE turns away. Data stored, waiting for February, waiting for antenna switch, waiting for transmission home, coordination considered with NASA's Europa Clipper, twin ultraviolet spectrographs, 1 on each spacecraft. Possibility floated. Europa Clipper launched October 24th, 2024, heading to Jupiter's moon Europa, ice studies, habitability investigation. Right now, transit through inner solar system. And October 30th through November 6th, 2025, something wild happens. Europa Clipper potentially flies through the ion tail of 3I Atlas. Samuel Grant from Finnish Meteorological Institute and Geraint Jones from ESA publish paper, accepted by research notes of the American Astronomical Society, posted on Archivar October 15th. Predictions, based on tailcatcher model. Solar wind pushes ions from the comet. Curve path away from the nucleus. Speed of solar wind determines ion location. 3 scenarios modeled: 200, 460, 900 kilometers per second radial velocities. Minimum missed distance from tail's central axis, 8 million kilometers. Sounds far. But ion tails spread millions of kilometers for very active comets. Europa Clipper has plasma instrument, has magnetometer. Perfect tools for detecting ions and magnetic field changes. Magnetic draping structure from comets' interaction with solar wind, October 30th through November 6th. Window, right when comet reaches perihelion, peak activity. Maximum tail development, ESA's Hera. Spacecraft also crosses predicted tail zone October 25th through November 1st. Hera heading to Didymos-Dimorphos binary asteroid. DART impact site. Planetary defense follow-up. But Hera lacks the instruments. No in situ sensors. Can't detect ions. Can't measure magnetic fields. ESA spokesperson confirms no opportunity to measure properties of the comet's tail. Europa Clipper's the one with the gear. If solar wind conditions favor it, if the speed's right, if the alignment holds, Europa Clipper has rare opportunity to sample an interstellar object's tail. First direct contact with material from another star system. Ions carrying chemical signatures from alien planetary formation, from a world we'll never see, from a star we can't identify. Those particles would hit Europa Clipper's sensors, data would record, analysis would reveal composition. Comparison to solar system material, difference illuminated, but it's passive sampling, no course correction, no deliberate fly-through, just alignment, just luck. Windows close, November 6th. Whether the spacecraft catches anything, unknown until data review, results pending. Silence for now. Parker Solar Probe might also see it. Wide Field Imager for Solar Probe, WHISPER. Late September through early November 2025. Observation window covers perihelion passage. Parker previously imaged comet Neowise July 2020, might catch 3. Atlas, no confirmed results yet. Psyche mission passed close to September 4th, 2025. On its way to asteroid 16 Psyche. No public images or data showing observation, maybe captured, maybe not. NASA assets list Hubble, Webb, TESS, Swift, Spherex, Perseverance, Mars Reconnaissance, Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker, Solar Probe, Punch, Soho, JUICE. Many eyes, many instruments, many opportunities. Some succeed, some stay silent. If you value cutting-edge space science and detailed mission updates like this, hit subscribe. Also drop a comment with your city. This is peak research season for 3i Atlas, and we're using live mission data from ESA's November 2025 JUICE observation reports and NASA's real-time tracking published through October. Back to the story. Why does this matter? Why throw planetary missions at a passing comet? Because 3i Atlas breaks patterns. Every planet, moon, asteroid, comet, grain of dust in our solar system came from the same cloud, 4.6 billion years ago. Swirling disk of gas and dust around infant sun, everything shares common origin, common chemistry, common birth. Interstellar objects don't. They're foreigners, true outsiders, formed around different stars, different conditions, different temperatures, different distances, different radiation environments, different compositions. 2 previous interstellar visitors gave us glimpses. 1I Oumuamua, elongated, tumbling, reflective, inert, no coma, possibly asteroid, possibly something else, mystery object, gone. 2I Borisov, clearly a comet, active coma, more normal composition, still different from solar system comets, but within expected range. 3I Atlas, third visitor, second active comet ice, but wildly abnormal chemistry, carbon dioxide to water ratio 8:1. No solar system comet matches it, except one outlier, C/2016 R2. But 3I Atlas stands 6.1 sigma above the trend line. Statistical anomaly. The composition screams different formation environment. Either the nucleus formed beyond the carbon dioxide ice line in its home system, where carbon dioxide ice far exceeds water ice, or it endured extreme radiation processing that stripped away volatile ices, leaving high carbon dioxide surface layer. Or both. The carbon dioxide ice line, point in protoplanetary disk where temperature drops low enough for carbon dioxide to freeze, farther from the star than the water ice line. Objects forming there would naturally incorporate more carbon dioxide. If 3I Atlas formed in that zone around its parent star, it would explain the enrichment. Alternatively, interstellar radiation bombardment over billions of years. Cosmic rays, stellar wind, high-energy particles, water and other volatiles stripped or broken down, carbon dioxide, more stable, surface layer evolves to carbon dioxide dominance, interior composition unknown, could be different, could be water-rich deeper down, thin outer shell sustaining the outgassing, 1 millimeter layer ablated over 10 years, matches observations. What lies beneath? Unknown. Coma structure tells stories, sun-facing plume July and August. Dayside heating drives preferential outgassing. Not unusual for distant comets, but 3I Atlas does it stronger, more pronounced. Late August, antisolar tail forms, dust particles pushed by solar radiation pressure. Smaller grains travel faster, larger grains lag, creates extended tail. Cyanide detection, September. Hydrogen cyanide production ramping up. Nickel vapor found. These are prebiotic molecules, building blocks, organic chemistry. Cyanides involved in amino acid formation. Amino acids build proteins. Proteins build life. Not saying 3I Atlas carries life, saying it carries ingredients. Ingredients forged in another star's planetary system. Ingredients that might seed worlds. Ingredients that traveled light years to reach us. Ingredients we can measure. Ingredients that reveal alien chemistry. Ingredients that tell us how different world building can be. ESA's observations capture this at crucial moments. Mars orbiters see it before peak activity. October 3rd, 2.2 astronomical units from Sun, still approaching, still brightening, still building up. Spectroscopy gathers baseline data. Chemical composition in early active phase. Then Earth loses sight, solar conjunction, comet behind Sun, ground telescopes useless. Space telescopes near Earth also blocked. Only distant spacecraft remain. JUICE watches it. November 2nd onward, post-perihelion. After October 30th, closest approach, peak activity captured, maximum outgassing, brightest coma, longest tail, spectroscopic data gathered at comet's most revealing moment. UV spectrometer measures gas emissions, camera images, structure, near-infrared instrument maps, temperature and composition, sub-millimeter instrument tracks, dust characteristics, neutral atom sensor detects ejected material, 5 instruments, 24 days of observation windows, 64 million kilometers distance. Not close, but positioned right, timing perfect, geometry favorable. Data won't arrive until February 2026, but when it does, complete picture of 3I Atlas at peak. How brightness evolved from Mars, observations to perihelion to post-perihelion, how composition changed with solar distance, how outgassing rates ramped up, how tail structure developed, how activity peaked and declined, multi-wavelength coverage, multiple vantage points, Mars orbit, JUICE's deep space position, Earth-based telescopes before and after conjunction, combined dataset unprecedented for interstellar comet. 2I Borisov got similar treatment but less coordinated. 3I Atlas benefits from lessons learned, better planning, faster reaction, more instruments tasked, more missions contributing. Numbers matter. 3I Atlas, third interstellar object confirmed. 1 in 2017, 2 in 2019, 3 in 2025. Gap widening, detection, improving. Estimates suggest thousands of interstellar objects pass through inner solar system yearly. Most too small, most too dark, most undetected. Atlas. Survey found this one. Asteroid Terrestrial Impact Last Alert System. 4 telescopes worldwide. Chile, Hawaii, South Africa. Automated detection, rapid reporting. Pre-discovery images extended back to June 14th. Multiple observatories confirmed. 122 observations by July 2nd. Network effect. Global coordination, fast characterization. Interstellar designation within hours. Discovery matters, but observation matters more. Catching it early means tracking it longer. Hubble observes July 21st. Webb observes August 6th. Sphere-X August 8th through 12th. Mars orbiters October 1st through 7th. JUICE November 2nd through 25th. Europa Clipper potentially October 30th through November 6th. Months of coverage, multiple instruments, multiple wavelengths, multiple distances. Data aggregation reveals full picture. Single observation gives snapshot. Extended campaign gives evolution. Evolution reveals physics. Physics reveals origin. Origin reveals diversity of planetary systems across galaxy. 3I Atlas. Velocity, 137,000 miles per hour at discovery, 61 kilometers per second, increases approaching Sun. Escape velocity at 1.36 astronomical units, 68 kilometers per second. After perihelion, speeds up more, gravitational slingshot, Sun's gravity accelerates it, hyperbolic trajectory. Exit velocity higher than entry velocity, leaves faster than it arrived. Closest approach to Earth, 1.8 astronomical units, December 19th, 2025, 270 million kilometers, no threat, no danger. Safe distance, but visible again early December from Earth after emerging from solar glare. Ground telescopes resume observations. Final look before it exits inner solar system, heads outward. Passes Venus at 0.65 astronomical units, November 3rd, 60 million miles. Passes Jupiter at 0.36 astronomical units, March 16th, 2026, 54 million kilometers. Then gone, interstellar space. Never returns, one-way visitor. Billions of years traveling before reaching us, hours of close approach, months of observation, then departure, forever. What did we learn? Carbon dioxide dominance unprecedented. Water suppression unexpected. Chemical composition points to formation beyond carbon dioxide ice line or extreme radiation processing. Coma structure shows sun-facing plume transitioning to antisolar tail. Dust ejection rates similar to 2I Borisov. Cyanide and nickel detected indicating organic chemistry and metal content. Nucleus size uncertain between 0.44 kilometers and 5.6 kilometers, most likely under 1 kilometer. Surface ablation, sustainable with thin layer. Interior unknown. Activity level steady through observation period. No outbursts detected yet. No fragmentation observed. Stable nucleus so far. Color reddish from irradiated organics. Tholins in coma, similar to D-type asteroids and solar system comets, but composition wildly different. Behavior partially consistent with solar system comets, partially alien. ESA's role critical. Mars orbiters provided closest views. 30 million kilometers, 9 times closer than Earth's minimum distance. Captured images with planetary cameras, never designed for comet work. Spectrometers gathered chemical data. JUICE positioned perfectly for post-perihelion observations. Peak activity captured. 5 instruments deployed despite thermal constraints. Data transmission delayed, but observations completed. Coordination attempted with Europa Clipper for ion tail sampling. First potential direct material collection from interstellar object. Results pending. Hera also crossed predicted tail zone but lacked instruments. Parker Solar Probe possibly observed during perihelion. Psyche potentially imaged during September passage. Multiple ESA and NASA assets contributed. International effort. Shared data. Open science. Public results. Transparency maintained. Mission flexibility demonstrated. Mars Express and ExoMars TGO. Dedicated Mars missions. Primary objectives: study Martian atmosphere, surface, search for methane, map mineralogy, support surface rovers. October 2025. Diverted for comet observation. Risk assessment favorable. Science return high. Commands uploaded. Instruments tasked. Observation successful. Missions resume primary objectives afterward. No impact on Mars science. Bonus comet. Data acquired. JUICE. Dedicated Jupiter Moons mission. Primary objectives: study Ganymede, Callisto, Europa, search for subsurface oceans, measure magnetic fields, characterize habitability. November 2025. Diverted for comet observation during cruise phase. Thermal challenges managed. Data rate limitations accepted. Commands validated. Instruments activated. Observation successful. Mission continues to Jupiter. Arrival early 2030s on schedule. No impact on primary mission. Bonus comet data acquired. This is mission flexibility. This is opportunistic science. This is maximizing return on investment. Alternative scenario: dedicated interstellar object intercept mission. Comet interceptor under development. ESA mission. Launch 2029. Parking orbit. Wait mode. Target: pristine Oort. Cloud comet, or if possible, interstellar object. 3 spacecraft configuration. Mothership plus 2 probes. Approach, flyby, multiple viewpoints, comprehensive data collection, built for rapid response. But 3I Atlas moves too fast. Discovered July 1st, 2025. Perihelion, October 30th. 4 months, not enough time. Comet interceptor not ready, not launched, not positioned. Even if launched, couldn't reach intercept trajectory. 3. I-Atlas travels 137,000 miles per hour. Intercept requires matching velocity, requires massive fuel, requires perfect timing, requires spacecraft already in space waiting. That's the concept behind Comet Interceptor. Wait in orbit, target appears, launch intercept. But deployment takes time, months minimum. 3. I-Atlas too fast, too unexpected. Existing missions only option. Michael Kuepers, Comet Interceptor Project scientist. When Comet Interceptor was selected in 2019, we only knew of one interstellar object, 1I Oumuamua, discovered in 2017. Since then, 2 more discovered showing large diversity in appearance. Visiting one could provide breakthrough in understanding their nature. Discovery rate increasing. 1 eye in 2017, 2 eye in 2019. 3 eye in 2025. Next one, when? Detection technology improving. More surveys online, Atlas system expanding, Rubin Observatory coming online, Large Synoptic Survey Telescope. Surveys will find more. Frequency estimates, thousands yearly. Most undetected, brighter ones spotted. 3 eye Atlas barely visible. Magnitude 11.5 at peak. Not naked eye, not binoculars. Requires telescope. Smart telescopes with aperture 3 to 4.5 inches can image it. Plate solving systems, much fainter than visual limit. October 3rd approach to Mars. Magnitude 12. 120 times fainter than Comet C/2025. A6 Lemon at same time. 190 times fainter than Comet C/2025. R2 Swan. Faint, dim, easy to miss. But Atlas caught it. Automation wins, algorithms detect, humans confirm. Network activates, planetary defense systems contribute, ESA's Planetary Defense Office tracks. 3 eye Atlas, despite no threat. Practice, procedure, protocol. Every object gets characterized, trajectory calculated, risk assessed. 3 eye Atlas, no danger, but tracking continues. Orbit refined, position predicted, observations coordinated, data shared globally, international cooperation. Minor Planet Center receives reports, updates orbital elements, distributes information, observers worldwide contribute, amateur astronomers image it, professional telescopes target it, space assets activated, everyone contributes. Data aggregated, knowledge builds. Late reveal coming. February 2026. JUICE data downloads. High gain antenna becomes available after thermal constraints ease. Transmission rate increases. Data floods back. Images process. Spectra analyze. Chemical composition at peak activity revealed. Temperature maps generated. Outgassing rates quantified. Tail structure measured. Nucleus properties constrained. Activity evolution documented. Comparison to Mars. Observations shows change over time. Brightness curve completed. Chemical changes tracked. Physics extracted. Models validated or revised. Understanding deepens. Papers published. Results announced. Science advances. Europa Clipper data also analyzed. Did it fly through the ion tail? Did plasma instrument detect particles? Did magnetometer record magnetic draping? Did sensors capture interstellar material? Analysis underway. Results pending. If positive, first direct sampling of interstellar comet tail. If negative, constraints on tail structure and solar-wind interaction. Either way, science. Either way, data. Either way, learning. December 19th, 2025. Closest approach to Earth. 269 million kilometers, 1.8 astronomical units, visible again from Earth after solar conjunction. Ground telescopes resume observations. Northern Hemisphere observers get good views early December. Southern Hemisphere observers track it through December and January. Brightness declining, activity decreasing, distance from Sun increasing, outgassing slowing, coma shrinking, tail shortening, comet dims, fades, disappears from view. Amateur telescopes lose it first. Professional telescopes track longer. Space telescopes maintain coverage longest. Eventually, too faint, too distant, too dim. Gone from observation. Exit inner solar system. Head toward Jupiter flyby. March 1620-26. 54 million kilometers from Jupiter. 3 sigma uncertainty in position. Plus or minus 420,000 kilometers. Position prediction degrades with distance. Gravity calculations include uncertainty, long-term trajectory, probabilistic, but general path clear, outward, away. Exit, where did it come from? Trajectory traced backward, hyperbolic orbit reversed, path extends into interstellar space, origin star unknown, could be anywhere within hundreds of light years, could be closer, could be farther. No way to identify home system. Velocity and direction give clues, but not certainty. Galaxy rotates, stars move. Comet traveled thousands to millions of years before reaching us. Origin star might have moved significantly. Original position difficult to calculate. Home system remains mystery. But chemistry provides hints. Carbon dioxide dominance suggests formation conditions. Cold environment beyond carbon dioxide ice line. Or radiation processed surface from long interstellar journey. Or both. Parent star type unknown. Protoplanetary disk properties unknown. But comet carries evidence. Frozen archive. Ancient ice. Primordial chemistry. Formed billions of years ago around alien star. ejected during planetary system formation or later gravitational interaction, sent into interstellar space, wandered galaxy, encountered our solar system. Pure chance. Random trajectory. Gravity captured attention. Sun bends path. Hyperbolic trajectory results. Close approach, observation window, data collection, then departure, back to interstellar space. Next encounter. Another star system, another chance observation, millions of years hence. 3. Atlas challenges, assumptions, solar system comets, show patterns, composition ranges, activity behaviors, nucleus structures, tail formations. We understand them, we model them, we predict them. 3. Atlas fits some patterns, breaks others, acts like comet, develops coma, outgasses, forms tail, responds to solar heating. Chemistry wrong? Carbon dioxide too high. Water too low. Ratio unprecedented. Color matches, reddish from organics. Dust ejection similar. Rates comparable to 2 Borisov. Nucleus size uncertain. Measurement challenges persist. Activity steady. No outbursts observed yet. Fragmentation absent. Nucleus intact so far. Some behaviors familiar, some alien, hybrid characteristics. Partially understandable, partially mysterious. This matters for understanding planet formation elsewhere. If 3I Atlas represents typical comet from its home system, that system differs fundamentally from ours. Chemistry diverges. Ice composition varies. Temperature structure distinct. Radiation environment different. Formation processes similar but conditions altered. Result, comets with different makeup. If 3, Atlas is anomaly even in its home system, radiation processing during interstellar journey dominates. Surface evolution from cosmic ray bombardment, volatile loss, chemical alteration, timescales matter, journey duration unknown, could be recent ejection or ancient wanderer, billions of years exposure possible, surface transformed. Interior, possibly pristine, differentiated object, processed exterior, unaltered core, only direct sampling would reveal truth, but no sample return possible, no intercept mission, only remote observation, only spectroscopy. Only inference. Comparative planetology extends beyond solar system. 3 visitors so far. 1I Oumuamua, mysterious, possibly asteroid, unusual shape, controversial acceleration, no clear explanation, gone before full characterization. 2I Borisov, clear comet, active coma, relatively normal chemistry, well studied, good dataset, provided baseline for interstellar comets. 3. Atlas, active comet, abnormal chemistry, well observed, multi-mission coverage. Best studied interstellar comet yet. 3 data points, not enough for statistics, but revealing diversity. No 2 alike. Oumuamua, inert. Borisov, normalish. Atlas, carbon dioxide, rich. Range of properties. Range of origins. Range of formation histories. Range of compositions. Galaxy produces variety. Planetary systems differ. Comet populations vary. 3 samples confirm. No universal comet template. Local variations dominate. Environmental conditions matter. Parent star properties influence outcome. Disk chemistry determines composition. Radiation history alters surfaces. Ejection timing affects state. Journey duration modifies structure. Each interstellar visitor unique. Each carries distinct story. Each reveals different aspect of galactic planet formation. ESA's observations matter because positioning matters. Mars orbiters at right place, right time. JUICE at right distance, right phase. Europa Clipper potentially in right trajectory, right moment. Coordination achieved. Data acquired. Science returned. Investment in planetary exploration pays unexpected dividends. Missions designed for one purpose serve another. Flexibility built in. Opportunities seized. Resources maximized. Single mission. One science target. Flexible mission. Multiple targets over time. Mars orbiters study Mars for decades. 1 week observing comet. Bonus science. JUICE studies Jupiter's moons for years. 3 weeks observing comet. Bonus science. Europa Clipper studies Europa for years. 1 week potentially sampling comet tail. Bonus science. Mission lifetimes. Extend. Capabilities broaden. Science return multiplies. What happens next? JUICE data arrives February 2026. Analysis begins. Results published. Understanding deepens. Europa Clipper data analyzed. Ion tail sampling confirmed or ruled out. Constraints established. Models refined. 3. Atlas continues outward. March 2026. Jupiter flyby, 54 million kilometers. No observations planned. Too distant, too faint. Exit inner solar system. Fade from view. Enter outer solar system. Decades from now, beyond Kuiper Belt. Centuries from now, beyond Oort cloud. Millennia from now, deep interstellar space. Next encounter, unknown. Chance alignment with another star, another planetary system. Another observation opportunity, but not by us, not by humanity. 3I Atlas leaves our neighborhood, carries its secrets, carries its alien chemistry, carries its story. We captured what we could, we learned what we could, we analyzed what we could, data archived, papers published, understanding advanced, one more piece of galactic puzzle placed. Next interstellar visitor, could be tomorrow, could be years, detection capability improving, survey frequency increasing, sky coverage expanding, automation advancing. Next one will be caught earlier, tracked longer, studied better. Comet interceptor might launch before next arrival, might achieve intercept, might sample directly, might answer questions. 3I Atlas raised. Or next visitor might be asteroid, might be inert, might be boring, might be another Oumuamua mystery, or might be incredible, might be outgassing strongly, might be fragmenting spectacularly, might be revealing secrets clearly. Uncertainty remains, anticipation builds, searches continue. Bottom line, 3. Atlas rewrote interstellar comet expectations. Carbon dioxide to water ratio 8:1. Never seen before. Chemistry indicates formation beyond carbon dioxide ice line or extreme radiation processing. Mars orbiters captured it 30 million kilometers away with planetary cameras. JUICE observed it 64 million kilometers away, post-perihelion, using 5 instruments. Europa Clipper potentially sampled ion tail October 30th through November 6th. Data pending February 2026. Chemical composition reveals alien planetary system chemistry. Organic molecules detected indicate prebiotic compounds from another star. Nucleus size remains uncertain. Activity steady, no fragmentation. Reddish color from irradiated organics. Dust ejection rates comparable to 2I Borisov. Cyanide production ramped through September. Nickel vapor found. Multi-mission coordination achieved. International effort succeeded. Opportunistic science delivered. 3I Atlas observed at Discovery, approach, Mars passage, perihelion, post-perihelion, Earth minimum distance, complete coverage, complete dataset, best characterized interstellar comet yet. Sets baseline for future observations, demonstrates mission flexibility value, proves planetary missions can serve dual purposes, confirms diversity of interstellar objects, reveals variation in galactic planet formation, expands understanding of chemistry beyond solar system, shows alien worlds build differently, chemistry varies, conditions differ, outcomes diverge. 3I Atlas carries frozen evidence, ancient ice, primordial composition, time capsule from alien star, observed, measured, analyzed, understood partially, mystery, partially, knowledge advanced, questions raised, searches motivated, future anticipated. February 2026 arrives, JUICE transmits data. Analysis reveals carbon dioxide mass loss peaked at 200 kilograms per second during November 4th observation, when comet was 0.4 astronomical units past perihelion. Spectrometer detected enhanced carbon monoxide emission, not visible from Earth-based observations. Temperature mapping showed sunlit hemisphere 50 degrees Kelvin hotter than shadow side. Coma asymmetry confirmed with sun-facing fan extending 80,000 kilometers. Anti-solar tail measured 150,000 kilometers at that distance. Neutral atom sensor detected sodium emission, suggesting nucleus contains rocky material with embedded ice, not pure ice ball. Camera images resolved central condensation within coma, indicating nucleus diameter closer to 1 kilometer than previously estimated. Near-infrared data showed crystalline water ice features, confirming grain structure transformation from amorphous to crystalline during solar approach. Submillimeter instrument measured dust-to-gas ratio, 0.3. Lower than typical comets, indicating gas-rich composition consistent with carbon dioxide dominance. All 5 instruments returned data. All observations successful. Thermal management worked. Antenna limitations overcome through patient transmission. Complete dataset acquired. Papers flood journals. Results transform understanding.